Okay, let's continue this idea of extremes and add a little bit more about the processes. Paul O'Gorman has been writing a lot of good papers on total precipitation and precipitation extremes under climate change, including model analysis, scaling, and so on. So we'll look at a few points from his paper from this special issue of Current Climate Change Report, edited by Adam Sobel and Susanna Camargo, I think, but you can look it up. So looking at the observations, here are sensitivities of observed annual maximum daily precipitation over land. These are solid lines with circles, and the dotted lines here show 90% confidence interval, which is computed with some method. And here it is done in 15-degree latitude bands relative to a global mean surface temperature, or here mean surface temperature over the 15-degree latitude band. The precipitation is from HADEX2. Sensitivities are calculated for grid boxes with at least 30 annual values, and the median sensitivity is plotted for each 15-degree latitude band. And you can see here oops, I cut off the latitudes here, but you can see it's the same here, going from -40 to 70 degree north, so 40 south to 70 degree north or so. And what else here? Temperatures over land and ocean from NOAA MLOST, and for B, the temperature time series were smoothed with a 9-year running mean filter. Why is this kind of statistical analysis done? Basically, as before, there are two things. One, we want to find extremes on land, but we want to see where the forcing comes from, which is of course from land and ocean, and you want to see what are the global impacts and what are the regional impacts. So if you look at 15-degree latitude band, then you want to see whether the scales you expect around it of 15 degrees is going to have a scaling impact or versus the global temperature. There is regression of the observed annual maximum daily precipitation. So the idea is to derive sensitivity in terms of percentage change in extremes, as defined here is the annual maximum daily precipitation per Kelvin warming. Okay, and we are always doing this, looking for whether it remains close to Clausius-Clapeyron, which is per Kelvin warming saturation vapor pressure goes up by 7%, and we want to see how that translates to extremes in terms of scaling per Kelvin warming. We already saw that when we did precipitation constraints, that tends to be lower than the Clausius-Clapeyron, which means extremes can happen, and some local dynamic feedbacks can drive strong vertical motions to create what is called super Clausius-Clapeyron scaling, or greater than 7% per degree of warming. Of course, if you're on land, warming can end up resulting in moisture limitations, so that could also control the extremes overall. In other words, the processes are complicated, and there are some arguments made for scaling based on observations and from models, but there are still a lot of questions, and we'll look at some of those questions as we go forward with this lecture series. Okay, so what are the points being made here? So sorry about cutting off the latitude here, but you can see at the southern tip here the sensitivity goes to 0 with a large uncertainty going from about -5 to about 3%, and the sensitivity increases, reaches almost 15% here, and you can see that it's larger in the tropics and then drops off towards the high latitudes in the northern hemisphere and increases again in the mid latitudes. Okay, this is when you look at the global temperatures, land and ocean. Whereas if you restrict the temperature regression to mean surface temperatures over the 15-degree latitude band, you get somewhat similar answers at mid-latitudes and the southern hemisphere subtropics, but the tropics here change character even though they still remain peak, but the uncertainty is still the highest in the tropics, basically because there is data issues, and then there are issues of just resolving the timescales. Remember, you have different large-scale processes controlling precipitation processes in the mid-latitudes, as opposed to the fast, small-scale convective motions that are resulting in precipitation and extreme precipitation in the tropics. So there is the data issue, and you get a slight flattening and a slight asymmetry here when you look at the 15-degree latitude band temperatures versus global temperatures. Okay, what else can be said? We can then try to find processes that lead to precipitation extremes. So that's the expression that Paul Gorman, Tapia Schneider and group have derived over time. And so it's a function of the so-called precipitation efficiency, the amount of rain that actually falls to the surface versus amount of condensation that happens in the atmosphere, which means there is some condensed water vapor being carried out of the of the atmospheric column as clouds, or re-evaporation and other processes that prevent the precipitation from reaching the ground. And this expression here in the curly brackets is an integral, which is given this way: 1 over g surface to 100 hectopascal. So you're integrating over the atmospheric column with a vertical velocity in the pressure coordinate, so it's negative as you go up, pressure decreases, and dqs dt, dqs as a function of temperature, dp with constant theta e star, so moist potential temperature and the saturation water vapor pressure change along the constant moist adiabat, basically integrated in the pressure coordinate. Okay, so when you think about the processes then which affect precipitation extremes, whether in natural climate variability like an El Nino, for example, or global warming, precipitation efficiency can change. For example, during an El Nino there is overall warming, but net precipitation over land decreases, but that's the total, not the extremes. So how can you use precipitation in an El Nino event as an analogy for global warming? We talked about this in the previous podcast, where we tried to use large-scale variability and change for constraining precipitation extremes, right? Vertical velocity is the dynamic part, so the circulation can include large scale, like in the mid-latitudes, and in the tropics it can include both large scale and small scale vertical motions related to organized mesoscale convective systems and typical tropical convection, which tends to be very small within organized large scale circulation. So obviously that's also a difficult thing. And then the question is about how saturation water vapor pressure changes with temperature. And obviously near the surface it can be Clausius-Clapeyron, especially over the ocean, but also depends on whether relative humidity can change or not. On land it does. So the humidity change itself with temperature can depend on where you are, near the surface or above in the atmospheric column, and so on and so forth. So this is kind of a theoretical attempt to understand precipitation extreme scaling with warming, given from the microphysics perspective as precipitation efficiency, dynamic perspective as the vertical motion capturing the essence of precipitation process, and the thermodynamic effect in terms of humidity. Okay, this is what is typically done to find the scalings. So here again, looking at the models now, sensitivity of the 99.9th percentile of daily precipitation to global mean surface temperature for climate change under RCP 8.5 scenario, which is 8.5 watts per meter squared imbalance resulting in 2100 from the representative concentration pathway, which basically corresponds to the business as usual scenario. Unfortunately, that's what we are on right now. None of the 25 years of negotiations have turned down the emissions yet. So those are from CIMIP 5 global climate model simulations. Shown are the multi-model median here in the green line, with the circles, and the full model range. So here is the dotted lines where a suite of models are taken. So again, you can see that in the tropics the uncertainties or the range of the models is very high because the models are coarse resolution, and these extreme processes in the tropics are essentially very small scale, and so we are looking at unresolved processes adding to the range of uncertainties, which basically result from convective parameterizations, deep cumulus convections. Okay. Also shown are the sensitivities inferred by constraining the model sensitivities using observations of tropical variability. So here you are, a constrained estimate of the sensitivity of extreme precipitation defined as 99.9th percentile of daily precipitation to global mean surface temperature. Global mean surface temperature, which is what we are most interested in. Okay, with a 90% confidence interval is shown here with some statistical method called bootstrapping, which I won't go into. Again, this indicates that we are basically struggling with observational uncertainties in these observational estimates of sensitivity of extreme precipitations, which is somewhere closer to Clausius-Clapeyron in the subtropics, increases to super Clausius-Clapeyron here in the mid-latitudes, and in both cases, well, here it's a little bit closer to Clausius-Clapeyron when we use regional temperature sensitivities. In the tropics it's higher, again potentially related to the dynamical feedbacks. Once the vertical motion is enhanced, let's say by global warming, dynamical feedbacks can increase this extreme precipitation, and here again it's super Clausius-Clapeyron. So always compare to the 7%, and if it's higher you call it super Clausius-Clapeyron. So basically the message is that precipitation scaling is closer to Clausius-Clapeyron in some places and is super Clausius-Clapeyron in many places, and depends on whether you're in the tropics or mid-latitudes. Models do mid-latitudes better because sensitivity to convective parameterization is lower there, and the eddy fluxes associated with the baroclinic instabilities, which are the main processes there. Remember the angular momentum breaking down baroclinic instabilities, the storm tracks, and so on, together create a better rendition in models. So you can see that the range in the models gets much closer at both latitudes here. There are also issues about subtropics where you are evaporating and sending the moisture away, but those trends are a separate issue that I'm not going to get so much into, because I'm mostly trying to focus here on the monsoon extremes, and it turns out that we have to also look at short duration extremes, which are very critical for urban flooding and flash flooding in other regions as well. So we will do that in the next podcast. So the main message here is that precipitation extremes under climate change will depend on latitude, on how you compute the sensitivities or scaling in terms of precipitation increase per Kelvin. And the other point to be made from Paul O'Gorman's paper is this one, where we are looking at intensity and again sensitivity at different frequencies. So I'll introduce this point and come back to some details of this short duration precipitation events in the next podcast. The 99.99th percentile of precipitation for different durations, so instantaneous, 1 hour, 3 hour, 6 hour, and daily. And the main point is that you can see the intensity drops, but the sensitivity is a little bit all over the place depending on the temperature you are looking at. This is from simulations of radiative convective equilibrium, what are called RCE models, with the cloud resolving model providing the local circulation. So radiative convective equilibrium doesn't have large scale circulation, but it requires local convective scale motions which are prescribed from cloud resolving models as selected at mean surface air temperature given here in these different legends. The sensitivity of the 99.99th percentile of precipitation to mean surface air temperature changes for the same temperatures shown in A. So the natural logarithm of the 99.99th percentile of precipitation as a function of mean surface air temperature from 10 simulations is linearly interpolated to a uniform grid in temperature, and sensitivities are calculated as the changes for a 3 Kelvin warming. So microphysics, dynamics, thermodynamics, and it also depends on the duration. So intensity matters. So here instantaneous intensity is higher for all temperatures compared to lower or longer durations. As you can imagine, as you integrate in time, the moisture flux needs to come from further and further, so the intensity drops to 0th order. That's how I would interpret that. And you can see that as the temperature increases from 277 Kelvin to 304 Kelvin, 304 Kelvin, the intensity goes up at each duration, and the sensitivity is harder to interpret here. For example, 277 has the highest sensitivity, so at lower temperatures the sensitivities are higher. As I said before, at warmer temperatures on land, for example, there could be moisture limitations for driving extremes. So you can see that the 304 here has somewhat lower sensitivity around Clausius-Clapeyron, and 295 is somewhat similar, and that seems to be kind of the threshold where you switch. But here you have 286, which has high sensitivity for instantaneous intensity of rainfall, but drops off below both 304, 295 and 277 here. So essentially you have to be very clear about what processes could be driving the intensity and duration of precipitation extremes, and what the sensitivity is to warming. Okay, here 3K warming is imposed in these experiments. We will come back and say something more about these short duration extremes, but you get the point that either from observations or from models there are still lots of unknowns, even though you can robustly conclude that extremes and intensity of the extremes is increasing under global warming, even when we subtract out the natural variability. So obviously that's what we have to do. So a lot of the attribution exercises where extremes are explored for their probability or intensity or duration being affected by global warming always focus on these sorts of processes. So for future projections, of course, how precipitation in efficiency changes, how circulation and vertical motion changes, and how thermodynamic response and humidity, saturation, vapor pressure changes are all going to matter, and that's where the challenges come from, especially because extremes are essentially small scale, and short duration ones tend to be much smaller scale and much more impactful in terms of flash floods and so on.